All right, in this video, we're going to look at definite integrals using U-substitution. So a definite integral will ultimately become a value, right? It's not going to be a family of functions. It's going to be some value. So we might be thinking of area in these types of problems. So to get us started, what we're going to do is we're going to be told in this exercise what we should let U be in these indefinite integrals. And I just want you to notice how these integrals change into ones that are more manageable than what we originally see. So in example 1, we've got to evaluate this definite integral. Of course, that would mean we need an antiderivative for this function on the inside. They're recommending we let u be 4x squared plus 1. So let's do that. And then if I do that, then du becomes 8x dx. And I'm going to get a nice perfect substitution. So 8x dx is now du, and of course I'm letting my 4x squared plus 1 be my u. And so watch, I'm going to write down this indefinite integral, or this definite integral, but I'm going to leave out those bounds for the moment. So 8x dx becomes a du. Sometimes you're totally allowed to just put the du in the numerator. It's like you're writing 1 du. Okay, or you could put the du off to the side, it doesn't matter. And then I've got a u squared now down at the bottom. All right, so again, maybe I'll just write this to be a little more recognizable to those of you who haven't seen many of these. All right, so notice I've left off, though, the -1 and the 0. And the reason I've done that is because this integral was initially in terms of the variable x, right? Evaluate as x goes from -1 to x equals 0. In fact, many textbooks, older textbooks, will do something like that. It kind of makes it too cluttered, and it's obvious that it's in terms of x by the differential in here. But really, that's what it means. We're turning this problem all in terms of u. So we've basically done this transformation. We've got to transform those limits of integration as well. So when x is -1, let's just kind of note, this will be the only time I write this out so concretely, but so when x equals -1, note that u is equal to, well, you just plug in -1 into this relationship here, 4 times -1 squared plus 1, which is 5. So I'm going to put a 5 down here. And when x is equal to 0, u is equal to 4 times 0 squared plus 1, which is just 1. So this would be the integral we'd want to now do, and it's much more manageable than the original. So the instructions here are not to follow through, but just to transform the integral, not to evaluate. Let's just do a few more. I'll do them a little more quickly now that we've got the idea. So in this integral, they're letting us, recommending that we let u be 4x cubed minus 1. So therefore, du is 12x squared dx. It's almost a perfect substitution, except for the negative there. We're allowed to put in a negative ourselves, so if I put a negative there and there, then I will have a good substitution. So what does this integral become? I'll leave off the limits of integration. Negative 12x squared dx is what I'm calling negative du. So I'll throw the negative out here and put the du over there. And this was what I called u, so it's u cubed. And all this means I just need to update my limits of integration. So when x is equal to 0, u is 4 times 0 cubed minus 1, which is a -1. And when x is equal to 1, u is 4 times 1 cubed minus 1, which is 3. So the value of the original integral, which was in terms of x, will be the same as this one, which is easier to deal with. So we would do that one if we had to actually follow through. Let's do a few more, and then maybe we'll do one out fully below. They're recommending in this one we let u be x squared minus 1. So that means du is equal to 2x dx. Now I see a 6x dx, and I'm off by a factor of 3. So I'm going to times both sides of this by 3 so that I can make a good substitution that's clean. 3 du is equal to 6x dx. And now I can replace 6x dx with a 3u. and I'm going to replace, with, as they said, x squared minus 1 with a u, so that my more manageable integral will look like this. So x squared minus 1 becomes a u, so that's u squared. 6x dx is now 3 du. I'll put a 3 there and the du there. And now we update our limits of integration. So as if x is negative 1, u is negative 1 squared minus 1, which is 0. And when x is a 2, u is 2 squared minus 1, which is 3. All right, one last example. This one you might want to pause and try on your own. But if you've unpaused at this point, I'll do it out for you. So this becomes 8x du would be 8x dx. I see a 24x dx, and I'm off by a factor of 3. So if we multiply again by 3 du is 24x dx. And now I've got a clean substitution. So my limits of integration I'll leave to the end. My denominator is now going to be u squared. 24x dx is what I'm calling now 3 du, so maybe I'll put the 3 there, the du down there. X is 0. When x is 0, u is 4 times 0 squared plus 4, which is 4. When x is a 1, u is 4 times 1 squared plus 4, which is an 8. Okay, and so then we would proceed and do this more simpler definite integral rather than the original more complicated one. So let's do 2 examples full out, and that'll be enough, I think, for definite integrals here. So in this problem, I note that the denominator here is 4x squared minus 5, and the numerator is 8x. So I think I should let u be the denominator. So if u is 4x squared minus 5, then du becomes 8x dx. And that's a perfect substitution. So this integral is going to be, I'll leave off the limits of integration. 8x dx is now just du. So let's write that as 1 du, and the denominator now is just a u. And I'm going to integrate from 0 to 1. So when x is a 0, u is a negative 5. And when x is a 1, u is a negative 1. Okay, now if you're coming to this video, the antiderivative of 1 over u, you just got to note it's not ln of u, it's ln of the absolute value of u, for reasons I can explain in a later video, in particular that absolute value. This will allow us to plug in the values here, which are negative. So this becomes natural log of the absolute value of negative 1, which is natural log of 1 minus ln of the absolute value negative 5. Now the absolute value, natural log of 1 is 0, so this is just negative natural log of 5. Okay, how about this one here? Finish with this example. All right, so I see a I see an x squared minus 1 in the denominator here. And I see an x there as well. This one looks a little tricky. If I let my u be x squared minus 1, let's see what might happen there. So if I let u be x squared minus 1, then du is equal to 2x dx. Now, it seems as though my x is kind of in the wrong place. This might be a little trickier. I think I'm actually gonna fudge this a little bit because I think, this problem's doable, but not. It's the point of it is not what I'm going after here. So if you don't mind, let's edit this a little bit. I really wanted, I think, that x to be in the numerator there. So let's just kind of assert and make this look the way we want it to. All right. So now this will be a little better because I can say du over 2 is x dx. All right, and so this becomes, so that'll be a nice substitution. X dx is now du over 2. And my denominator there is going to be just a square root of u. And we'll update our limits of integration. So this becomes du over 2. So I'm going to put the 1/2 on the outside. I still have a fraction. Okay, that was all my way of kind of sprawling out the du over 2. And the denominator is the square root of now u. And now let's look at our relationship. When x is root 2, u is root 2 squared, which is 2 minus 1, which is 1. And when x is 2, u is 2 squared minus 1, which is 3. We now just need an antiderivative of 1 over the square root of u. So this is 1/2. Let's rewrite it in a calculus-friendly way. I think u to the negative 1/2 will make it easier to do an antiderivative. So this becomes 1/2. So I'm going to add 1. So that becomes a u to the 1/2, and then I'll multiply by a 2. That was, I think, an antiderivative of u to the negative 1/2. The 1/2 and the 2's cancel, which I'll show in a second. Right, so we can cancel those right now if we'd like. Okay, so let me just note that. Now it's u to the 1/2, integral from 1 to 3. And so it's the square root of 3 minus the square root of 1, which is root 3 minus 1. All right, so I edited that problem to be a little friendlier. Sorry about that, that I didn't have it worked out ahead of time. But that is how we use U-substitution to help us with definite integrals.